Example 3. The half-life of strontium-90 is 25 years. This means that half of any given quantity of strontium-90 will disintegrate in 25 years. So if a sample of strontium-90 has a mass of 24 milligrams, find an expression for the mass of T that remains after T years. So, first thing is first. We know that the mass is initially 24 grams and is halved during each 25-year period. So what does that mean? Well, that means that initially, that means the mass when the time is at 0 is 24. Now, for each 25-year period, since 0 represents T, now we want to go M of 25, because that would be 25 years. So, again, the half-life is disintegrating every 25 years. So that means that we're taking 1/2 of that 24. So it becomes 1/2 times 24. Now, if we go another 25 years, well, you add 25 to 50, so we're going to find M of 50. And so that equals 1/2, and that means we're multiplying it by another half times 24. So we can rewrite this as 1/2 to the second power times 24. Same thing over here. This is going to be 1/2 to the first power times 24. Now, what if we go another 25 years? Well, 25 after 50, adding 25 to that is going to give us 75. So that's 1/2 times 1/2 times 1/2 times 24. So now we're going to get 1/2 to the third power times 24. And then if we go a little further, for another 25 years, we have M of 100. So we have 1/2, another half, times another half, times an additional other half, times 24. And that gives us 1/2 to the fourth power times 24. So what can we say? Well, we can say that from this pattern, it appears that the mass is remaining after T years. M of T, which is equal to 2 to the power of T divided by 25 times 24. Now, we don't want to leave that in the denominator, so we want to write that as a variable raised to a negative power. So we're going to end up with 2 to the power of negative T over 25 times 24. So let's rearrange this function to be 24 times 2 to the negative T over 25. And now what we're going to do is we're going to factor out that T as an exponent. So it's going to be 24 times 2 to the negative 1/25 raised to the power of T. So let's write what the final function looks like. We have M of T, which is equal to 24 times 2 to the negative 1 divided by 25 raised to the power of T. So this is an exponential function with a base of 2 to the negative 1 over 25. Or we can say that this is 1 over 2 to the positive 1 over 25. Now let's take a look at the next question. The next question is asking us, find the mass remaining after 40 years, correct to the nearest milligram. So that means when t is equal to 40. So we can say that the mass that remains after 40 years, we're going to plug that into the function m of t, which is equal to 24 times t to the negative 1, 25 t. So we're going to plug that into 40. So we're going to have m of 40, which is equal to 24, 2 to the negative 1 over 25 to the power of 40, which is equal to 24 times 2 to the negative 40, 2 to the negative 40 over 25. So what does that give us? Well, let's go ahead and plug that into our calculator. So we have 24 times 2 to the power of negative 40 divided by 25, and then another parentheses. So if we round that to one decimal place, that is approximately 7.9. So what that means is that the mass that remains after 40 years is 7.9 milligrams. And again, this is the model that we got from our previous step. So let's take a look at part C. Part C is asking us use a graphing device to graph m of t, and then use the graph to estimate the time required for the mass to be reduced to 5 milligrams. So let's go ahead and put that in our graph. So we're going to use Desmos, and we're going to put this into our graph. So we have 24 times 2 to the power of negative t, or we're going to use x, and then divide that by 25, and then a parenthesis. Okay, so as you can see here, we're not able to see anything in our graph, but as we scroll a little further, we might be able to see what's going on here. So you might have to kind of move some things around, okay? And now the next step tells us that we want to find out, okay, the time that's required for the mass to be reduced to 5 milligrams. So that means that we need to graph when x is equal to 5. Sorry, not x is equal to 5, when y is equal to 5. Because that is the horizontal line. That's going to tell us the time that's required for it to decrease. So as this line is decreasing, when it's at 5 here, okay, what's happening? Well, we can take a look at where it intersects. So where does the graph intersect? Well, it looks like it intersects right here. So it looks like the time, if you look here, that the mass is at 5 milligrams, but then what is the time? Well, it's approximately 56. So from the graph and being able to find the intersecting point there, we can say that the mass of the sample will be reduced to 5 milligrams after about 57 years. And again, let's take a look at what that graph states here. That graph tells us that the intersecting point is at 56.5765, which approximately gave us about 57 years.